The best Python programs don't reinvent solutions. They bring together focused, reusable code that already does its job well. In this tutorial, we'll create and import our own module, organize related code inside a package, and use a third-party package installed with pip. Along the way, you'll learn how Python namespaces keep names organized, how different import styles affect your code, why wildcard imports can cause problems, and how to start using an unfamiliar package without memorizing everything inside it. Then we'll build and run a small project that demonstrates each type of import in practice. Reusable Python code generally comes from three places. First, Python includes a large standard library containing ready-made modules such as datetime, math, and many others. These are installed with Python, so we can import them without using pip. Second, we can write our own modules and packages. The module is normally a single Python file, such as the greetings.py file we'll create later during our demonstration. Related modules can be organized into packages, allowing a project to grow without placing all of its code into one enormous file. Third, we can use packages created by other developers. Packages such as Humanize are normally downloaded from the Python package repository, PyPi, and installed into a virtual environment with pip. Once installed, our program can import and use their public features, regardless of where the reusable code originated. Python's import system makes it available to our program. Each module should have a clear responsibility, and the modules grouped inside a package should serve a cohesive purpose. When modules and packages mix unrelated programming domains, they become harder to understand, test, reuse, and maintain. Keeping reusable code focused makes it easier for other programmers, and our future selves, to use with confidence. A Python module is normally a single file ending in .py. In this example, greetings.py is a module containing code related to greetings. We import the module with import greetings, leaving off the .py extension, and call its function as greetings.greet. The module name creates a namespace, making it immediately clear where the greet function came from. A package is a directory used to organize related modules. Here, TextTools is the package, and formatting.py is a module inside it. The empty init.py file identifies TextTools as a regular Python package. The bounding double underscores are important. Be sure to include them when you create your own packages. Empty initialization files are common. The code can remain in separate purpose-specific modules. We can import the module with import texttools.formatting and call its function as texttools.formatting.emphasize. That complete qualified name reflects the structure of the code. TextTools is the package, formatting is the module, and emphasize is the function. Modules keep focused code in manageable files, while packages organize related modules as a project grows. Their namespaces also show where names belong, making the code easier to understand and reducing the risk of unrelated names colliding. Humanize provides a useful real-world example of how a Python package can organize related code. Its package directory contains only 7 files, but each one has a distinct responsibility. FileSize.py handles readable file sizes. Number.py contains tools for formatting numbers. Time.py handles readable dates and durations. Lists.py creates natural language lists, while i18n.py provides language and locale support. The py.typed marker tells development tools that the package provides type information. Unlike the empty init.py file we'll create in our own simple package, Humanize uses its init.py to define a convenient public interface. It imports selected functions from the internal modules and exposes them directly through the Humanize namespace. For example, the natural size function is implemented inside FileIce.py, but Humanize's initialization file exposes it so we can simply import Humanize and call humanize.naturalsize. We do not need to know or remember which internal module contains the implementation. This is a common package design pattern. Keep the internal code divided into focused modules, then provide users with a simple, stable interface. Humanize is organized internally, but easy to use externally. There are 2 common ways to import and call the same function, but each one affects our program's namespace differently. The first approach is to import the module while preserving its complete package path. With import texttools.formatting, Python makes the module available through the texttools.formatting namespace. We then call the function as texttools.formatting.emphasize. This qualified form is longer, but the function's origin is always clear. It also presents a very low risk of name collisions because emphasize remains grouped beneath its package and module names. That clarity can be especially valuable in larger projects. The second approach is to import the function directly with from texttools.formatting. Import emphasize This places emphasize directly into the current file's namespace, allowing us to call it simply as emphasize. The direct form is shorter, easy to read, and convenient when a function is used repeatedly. However, another imported function, local function, or variable could also use the name emphasize. If that happens, one name may replace or obscure the other. Both approaches access the same function, and neither is universally better. The choice depends on whether brevity or a clearly qualified namespace is more useful in that part of the program. For our demonstration, we'll use the shorter direct form from texttools.formatting import emphasize. A namespace keeps names grouped according to where they belong. This allows different modules to use the same function name without interfering with each other. In this example, both reports.py and messages.py define a function named formatText. That is perfectly reasonable because each function belongs to a different module and performs a different kind of formatting. If we import the modules with import reports and import messages, the functions remain separated by their module namespaces. We call one as reports.formatText and the other as messages.formatText. Both functions remain available, their origins are clear, and Python has no trouble distinguishing between them. The situation changes when we import both functions directly from reports. Import format text places the first function into the current namespace under the name format text. The next statement, for messages import format text, places a different function under that same name. The later import replaces the earlier binding, so an unqualified call to format text now uses only the version imported from messages. Python does not necessarily display an error when this happens. One valid name has simply been replaced by another, which can make the problem difficult to notice. Qualified names preserve context and prevent ambiguity. Direct imports remain useful, but we should import names carefully and make sure their meaning stays clear within the current file. Python also allows a wildcard import written as from module import star. The asterisk tells Python to import all of the module's public names directly into the current namespace. This is valid Python, but it creates poor clarity. Looking at the import statement alone, we cannot easily tell which functions, classes, or constants were introduced. When one of those names appears later in the program, its origin may not be obvious. Wildcard imports also increase the risk of name collisions. An imported name can replace another imported function, a local function, or a variable using the same name. The problem can become even more surprising if a future version of the module exposes additional names that did not exist when our code was written. An explicit import avoids that uncertainty. With from texttools.formatting import emphasize, we know exactly which name enters main.py. The code is easier to read, easier to trace, and safer as the project grows. As a general rule, import the module itself or explicitly name what you need. Wildcard imports may occasionally appear in specialized code, but we normally avoid them in ordinary Python projects because they hide the namespace. Installing and importing are related, but they are not the same action. Installation happens at the terminal. When we run pip install humanize, pip finds the humanize package on the Python package index. PyPi downloads it and places it in the site packages directory of our active virtual environment. We normally install a third-party package once for each environment where it is needed. Installing humanize does not automatically make it available inside every Python file. To use it in a program, we add import humanize to that file. Python then finds the installed package inside the virtual environment and makes it available through the humanize namespace. Our program can now call public functions such as humanize.naturalSize. The installation provided the package to the environment. The import gives the current Python file access to it. So the distinction is straightforward. Install a third-party package into the environment and import it in each Python file that uses it. Standard library modules in our own local code do not require a separate pip installation, but they still need to be imported wherever we want to use them. Learning a new package does not mean reading all of its source code or memorizing everything it can do. The goal is to understand the part of its public interface that solves the problem in front of us. Start by identifying the package's purpose. Its description should tell us what kinds of problems it was designed to solve. Then visit its official documentation and look for a quick start guide or basic usage example. A small working example often teaches us enough to begin. Next, test one feature with a simple input. For humanize, we can import the package, pass a raw byte count to natural size, and confirm that it returns a readable value, such as 1.5 megabytes. Keeping the first experiment small makes any mistake easier to understand. When we need more detail, Python's built-in help function can describe a function's inputs, options, and behavior. The package's API reference can provide additional examples and explain important limitations. We only need to explore deeper documentation when the current task requires it. A package may contain many internal modules and implementation details, but ordinary users usually work through its public interface. We should understand what a function expects, what it returns, and any important limitations, but we do not need to memorize how every internal step works. Learn the interface, not every implementation detail. The purpose of reusable packages is to provide ready-made solutions that we can understand well enough to use correctly, without having to rebuild them ourselves. Now that you know how modules and packages work, let's try a quick demonstration. This is going to be fun. Our demonstration will be a complete tiny application that will highlight importing from the standard library, built into Python directly, a local module that we will create, a local package that we will create, and a newly installed Python package that we will install using pip. We'll begin by creating a new directory named imports_demo and moving into it. Then we'll create a virtual environment named venv and activate it. The virtual environment gives this project an isolated location for any third-party packages we install. If you'd like a more detailed explanation of virtual environments, you'll find that in the separate venv tutorial. We'll start our program with Python's standard library. Nano is a small text editor that runs directly inside the terminal, so we'll use it to create main.py. We import math, which is a standard library module included with Python. Since it is already included, we do not need to install it with pip. The import math statement brings the module into our program under the math namespace. We then call math.squareroot using that qualified name, which clearly identifies the module where square root originated. We'll save the file, exit nano, and run the program. The square root of 81 is 9, so our first import is working. Next, we'll create our own reusable module named greetings.py. A module is simply a Python file containing code that another Python file can import. This module has one clear responsibility, creating a friendly greeting. The short comment describes the function's purpose, and greet accepts a name and returns a formatted greeting. We'll save the module and return to main.py. This time, the nano command includes +1, 1. The first number tells nano to open the file at line 1, and the second tells it to place the cursor at column 1. Opening at a known position makes it easy for us to insert the new import alongside the existing one. We'll use from greetings import greet. Python finds greetings.py in our local project directory, and we omit the .py extension in the import statement. This direct import form takes the greet function from the greetings module and adds the name greet directly to main.py's namespace. That lets us call the greet function without placing the module name in front of it. This is shorter than using import greetings and calling greetings.greet. But it also means we must avoid creating or importing another name called greet. We'll save the updated program and run it again. It now uses both a standard library module and a module written locally for this project. Now let's organize related code inside our own package. We'll create a directory named texttools, then use touch to create its init.py file. That file is intentionally empty. Empty init.py files are common, and its presence identifies texttools as a regular Python package. The leading and trailing double underscores are important, so don't forget to use them. We'll keep the actual code in a separate module named formatting.py. This gives us 3 distinct levels. Texttools is the package. Formatting.py is now a module inside that package, and emphasize is a function inside that module. The function has one job, converting some text to uppercase and adding an exclamation point. Its purpose fits naturally inside a text formatting module. Back in main.py, we'll import it with from texttools.formatting, import emphasize. This import path follows the project's structure. Python enters the texttools package, finds its formatting module, and imports the emphasize function directly into main.py's namespace. The fully qualified alternative would be import texttools.formatting, followed by a call to texttools.formatting.emphasize. That longer form preserves the complete namespace and makes the function's origin especially clear. For this demonstration, we selected the shorter direct import form. After saving and running the program again, we can see output from the standard library, our local greetings module, and the formatting module inside our local texttools package. Our final example comes from outside our project. Humanize is a third-party package, so it is neither part of Python's standard library nor stored among the Python files we created locally. The pip install humanize command downloads humanize from the Python repository, PyPi, and installs it into the site packages directory inside our active.venv environment. Installing it makes the package available within this virtual environment, but it does not automatically import it into our program, or make it available outside of this environment. We'll return to main.py and add import humanize. Python searches its import locations, finds humanize inside our environment's site packages directory and makes it available through the humanize namespace. We'll call humanize.naturalSize with a raw value of 1,500,000 bytes. Because we retained the package namespace, the call clearly shows that natural size comes from the humanize package. When we run the completed program, we get 4 successful results, one from Python's standard library math module, one from our local greetings.py module, one from the formatting.py module inside our local text tools package, and one from the third-party humanize package installed inside the virtual environment. Finally, we'll display the completed project structure. The find command excludes the venv directory and Python's automatically generated PyCache directories, so we can concentrate on the source files we created. We now have main.py, one local module named greetings.py, and our text tools package containing an empty init.py and the formatting.py module. Humanize does not appear in this local source tree because it lives separately in the active virtual environment site packages directory. Together, these examples demonstrate the major sources of imported Python code: modules included with Python, modules we write locally, modules organized inside our own packages, and third-party packages installed into a virtual environment. We've rushed through a lot of information in this demonstration. You might want to review it a couple of times. Each time you see Python using the various forms of imports, the process will become more familiar. Eventually, it will become second nature for you. Our completed project demonstrates 2 ways to organize and import code that we write ourselves. First, greetings.py is a local module. It is one Python file with a focus purpose. The statement from greetings imports the greet function directly into main.py, allowing us to call it simply as greet. The text tools directory is our local package. Its empty init.py file identifies it as a regular Python package, while the reusable code remains in the separate formatting.py module. Empty initialization files are completely normal. To reach the function inside that package, we use from texttools.formatting import emphasize. The import path follows the code structure. Texttools is the package, formatting is the module, and emphasize is the function we are importing. Modules let us reuse code from individual Python files. Packages keep related modules organized as a project grows. In either case, write focused code, use meaningful names, and import only what the current file needs. Python's standard library contains modules that are installed along with Python itself. In our demonstration, math came from the standard library, so no pip installation was necessary. We imported the module with import math and used its namespace to call math.sqrt, the square root function. Third-party packages come from outside Python's standard library. They are commonly downloaded from the Python package index, PyPi, although some are distributed through other trusted project sources. Before Python can import one, we must install it into the active environment. We installed humanize with pip install humanize. Pip downloaded the package and placed it in the site packages directory inside our virtual environment. We then added import humanize to main.py and called humanize.naturalSize through the package namespace. The important distinction is where the code comes from. Standard library modules are included with Python. Third-party packages must first be installed for the environment where we plan to use them. After that, both use the same Python import system, import the module or package in every file that needs it, and use a qualified namespace whenever it helps keep the code's origin clear. A few best practices will keep modules and packages understandable as our projects grow. First, give each module one clear purpose, and keep every package focused on a cohesive area of responsibility. Code that mixes unrelated jobs becomes harder to test, reuse, and maintain. Use namespaces deliberately. Qualified names such as module.function preserve context and reduce the chance of collisions. Direct imports can make frequently used names more concise, but we should choose them intentionally. Import explicitly. Either import the module or name the specific functions, classes, or constants that the current file needs. We normally avoid import star because wildcard imports hide where names originated and may silently replace names already in the namespace. Keep init.py intentional. It can remain completely empty, as it does in our small text tools package, or it can expose a carefully selected public interface, as we saw with humanize. Neither approach is automatically better. The file should serve the package's design. Finally, learn a package through its public interface. Begin with official examples. Inspect relevant functions with the built-in help function and understand their inputs, outputs, options, and limitations. Read deeper into the implementation only when the task requires it. Clear structure and clear imports produce maintainable Python code that is easier for other developers and our future selves to understand and use. You now know how to use modules, packages, the standard library, and third-party packages. You've also seen how namespaces keep names understandable, why explicit imports are usually best, and how to begin using a new package through its public interface. If you'd like a deeper explanation of isolated Python environments, watch the Venv tutorial next. If you want to learn how to install, upgrade, remove, and record Python packages, the pip tutorial will take you through those commands step by step. You'll also find links to some recommended Python books in the video description. Thanks for watching Kendall's Tech Tutorials. If this tutorial helped you, please click like and subscribe for more practical Linux, Python, Django, and open source tutorials.